Hi. So today we're going to talk about limits. Are you reaching yours? We're going to progress from one-sided limits to two-sided limits to the formal definition of the derivative, since they all are linked together and how functions work and what they're doing at a point. Because normally you talk about like the overall function like this. You know how in algebra 1 or whatever they give you a line and it has a slope, and that slope leads into a very flat figure. And flat as I mean it's unchanging, whereas opposed to this one, you get a little bit of that curve, or this one, to infinity and beyond. Okay, sorry for clicking the back button. Man. Anyway, so we're going to start with this function, a one-sided limit. A one-sided limit literally means that what is the function doing as you approach it from one side or the other. Let me get my pen here. So a negative side, so like 2, the negative less than 2, less than 2, negative, but more than 2, 2.1, just so you can like visualize, since like negative you often assume on the left side of the number line, just like off the y-axis, but in reality it's just left and right of the point. That was a bit confusing to me sometimes. Anyway, and so for this point right here, it is approaching 1 on the left side. See how it gradually moves up, and then it jumps. And this point doesn't exist here because it's right there. Wow, magic trick, cats of the bag. And then it comes down here. So you'd say function g of x, as it approaches x from the left side, sorry. See, I even got messed up with that. 2 from the right side equals 1. And that's basically all you have to do. And of course, if it were to be from the right side, the positive side, it would be 2. I should write that in a better way since this is going to be the thumbnail, but at least you'll know what happened when you look at it now in retrospect. And so here we've got another function. This time, instead of the empty circle, hollow circle, solid circle, which signifies it leads up to the point, and then like there's where the actual point is when that happens, when the jump occurs. Now we're going to deal with limits where they approach positive and negative infinity. These both approach positive infinity, and that might some of you guys might think that means that it's the limit exists, since you think it like they all magically end up here, but in reality it'd be some sort of thing like 1 over x or something like that. But it would, or 1 over x squared, 1 over x minus 2. Oh, I'll redo this real quick. So this works, 1 minus x minus 2 squared. But at that point it doesn't actually exist. It's just that as you get closer to it, it's gonna skyrocket. And so here, what we can see is the limit, and let's see how. Okay, so for a limit to exist from both sides, it has to approach an actual point on both sides. So 2 from the negative side of f of x. Okay, I'm trying to speed run this here. Is positive infinity. You put a pause in front of here. Imagine if it was right in front of it. And for the positive side, it'd be like that as well. Negative positive infinity as well. Thing is, there has to be a finite point here, because that's a terrible arrow. I apologize. Because finite point actually exists. Infinity. None of you guys have an infinite amount of apples, infinite amount of any physical thing. So in terms of math, if it doesn't work in reality, it shouldn't work here. And so now we've understood how to explain when a function works and how it doesn't work. You can talk about a removable discontinuity when it goes like this, and there's the point's actually here, and then it continues. That's removable. You can just like plug the hole essentially. But if it's anything like these two, it's not removable. Oh my gosh, this is so many arrows. It's gonna look like the ravings of a lunatic. But let's continue. Now, let's talk about slope, right? And I picked these two drawings because overall they have the same average slope. Let's talk about this from the physics point of view, since that's the most intuitive, what you can wrap your head, what is the easiest to wrap your head around. Let's say 3 miles 3 meters, 3 hours, right? So t position, and that in the same amount of time, the car went the same amount of distance. Thing is, at this point, the car is moving faster, right? Because it's gaining position more rapidly. And that has something to do with the derivative, the slope at an instantaneous point. And you might be saying, wait, how do you find the slope at an instantaneous point? And if you're looking at this thing, it doesn't change. So you could say, oh, the slope's always 1, because the slope's 1 here at this point, slope's 1 here. It doesn't change. But for this line, it's 0 here. It's flat. Imagine this was perfectly flat. My drawing skills are severely handicapped. And then here, it's like maybe, let's say a 1.3. Ugly number, but that's how I see it. Bear with me. And so, let's talk about how you would find the slope. So, as we've done for years and years, we've used this equation. Sometimes people with the y1 there, it doesn't matter at all. It's just pairs. And so that's how you would find. You could also use that to find the average slope. Because where the slope doesn't change, you pick any amount of pick the difference between this point and this point. It's going to go up the same as if you pick the difference between this point and this point. Or it goes up, rise, for how much it runs. I don't know if you guys use that phrase, but that's how it was taught to me. Oh my gosh, that's an abomination of an R. But let's continue. So then, Salcon over here. Anyway, so now let's draw a smaller triangle. Let's try to find the average slope of this higher segment. Let's say it goes up. That's not a 1. These are such ugly numbers. I apologize to everyone watching. And this is like, that's really small. Even the axes aren't even, the same size. Let's say this is like 0.2 or something. This is a very sorry excuse. And then this is essentially like you multiply by 5 because it's like you're multiplying 0.7 divided by 1 over 5. Secret tip here. So wait, no, that's 0.35. Sorry. Anyway, that's the average slope. That's where we go, and we ignore this curve. Thing is, we can do this smaller and smaller and smaller. Watch. I'm going to zoom in to the max. And we're going to find this mini triangle. Let's do it somewhere where, let's do it. No, I don't mean to grab the 7. Let's do it at the top here. Let's make the tiny triangle. This is going to be like 0.0, let's say it's 0.07. Let's just say it's like a tenth of that. Up, and it's like point whatever. And we'd find that slope again. We'd find out that this is bigger. So let's say it's 0.09 here and 0.02, right? Because this looks steeper than that. This is going faster. It's gaining more position in less time. So, now that we've established that there is no real limit to how small we can set up our slope triangle, we can go about making the formal definition of a derivative. You might be asking me, what? You're saying I'm gonna draw a bunch of tiny slope triangles every time I want to make a point? That slope square, slope rectangle, but oh my gosh. But once you think about it, it's pretty natural. What was this? This is going to be hard to figure out what that was. Let's figure it out. So let's call this function z of x, because we're quirky and different. Let's say it's z of x. And let's think about it. Let's say I have z of x, but it's better, right? So let me move up. Let's say that we make a tiny slope triangle, right? Tiny. And it moves its h across on the bottom. And the cool thing about we only need to have one constant for the distance here, because if we have an equation, we just plug it in and find how much it runs. So we don't have to have like an h and a k or whatever. So if for any of you people extremely aggravated the fact that I didn't come up with another fun mini constant, but just h, teeny tiny, right? Because we want to find as close as we can to zero difference. So if I like zoomed in maximum, I'm already 400%, that you could find at that very instant. Like if you paused at the picosecond and you could instantly calculate the car's velocity. And now let's make a slope triangle, right? So this would be, that's the z2, or the y2, I'll call y2, excuse me, sorry. And let's find the y1, which would be the left side of the equation. Oh my gosh, minus, sorry. But I'm deriving this for you so that if there's any issue, it's because I'm thinking right now. Minus z of x, that would give you the horizontal run. So now, how do we find, I mean the horizontal, the vertical rise, because we're finding this point, and then this is finding that point right below it, and we're just minusing that distance. And now, simply to find what's the distance between x plus h and x. H! And so, we have our equation. Ba-boom! Ba-boom, boom, 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 boom. And so what often happens, I'm not going to give you an example since this is already 11 minutes. I don't know how, sorry. But that's your equation. You'll see an f of x. And what this means is that often in your equation, if you have an x squared or something, as opposed to an x, what will happen is the x squared term will cancel with this x squared term, but you'll get a 2xh. And then you'll have like another h term, like, h squared. But no one likes it. No one likes it because h is tiny. H doesn't do anything when it's on its own. But when it has a good old x by its side, it actually has value. Since what happens when you divide by h and you cross things out, you remove that power, you get 2x plus h as your slope anywhere, and if you plug that in. Actually, I did give you an example. I lied. The h doesn't matter because it's like 0.000000, and you have 2x. So next time you see a parabola, you can walk up to it, plug in a point, let's say it's 1, and the instantaneous slope at it, at 1, would be 2. It would be like, and now you're on your way. We did limits, one side, two side, that, I talked about removable, non-removable, and we figured out how it works using physics as an example. Thank you guys for watching. Hopefully I didn't ramble too long. Yeah.